So I don't know if I'll get through all section 4.1 today, but this is like a pretty quick section, just highlighting how subspaces could relate to one another by writing things in terms of orthogonality relations. So orthogonality of subspaces is going to be an important idea in chapter 4. And so what it means for two subspaces to be orthogonal, the definition will hopefully be pretty intuitive, and that we already have a notion of what it means for two vectors to be orthogonal in terms of the dot product. And so we're just going to extend that to the idea of vector spaces by considering the dot product of every vector between those two vector spaces. So we have that two vectors we know, v and w, are said to be orthogonal when v dot w ends up being equal to 0. So in terms of matrix multiplication, you can rewrite v dot w as v transposed times w. We'll look at an example later, which will hopefully make this a little bit more clear, how v dot w is the same as v transposed times w. So just writing things in terms of matrix multiplication. And so we're going to be concerned about the orthogonality for the following 4 subspaces that we talked about on Wednesday. So the 4 main subspaces so far in this class are the column space, the row space, which is really just the column space of A transpose, the null space of A, and then the null space of A transpose, which is sometimes called the left null space of A. And so what we're going to be showing today is that the row space of A ends up being orthogonal to the null space of A, and then the column space of A ends up being orthogonal to the left null space of A. And it really just follows from definition, or the definition of a null space. Okay, so what it means for two vector subspaces to be orthogonal to one another is we say that the subspaces V and W are orthogonal if we have that the multiplication of V transposed times W is equal to 0 for every single V and every single W inside of the subspace. So you look at every possible vector V and W in these subspaces, and then you want to see if they end up being equal to 0. And so this is why we talk about bases, and that it suffices to just check that the basis of V, like the vectors that make up the basis of V dotted with the vectors that make up the basis of W, are orthogonal. If you can show that ends up holding, then you can determine that the two subspaces are orthogonal. Because really, like, these subspaces are going to have infinitely many elements. So you want to reduce the number of calculations as much as possible. So let's look at an example. So we're going to define V to be the subspace of R3 defined by the following relation. So the subspace V is going to consist of all vectors of the form V1, V2, V3, such that V1 minus 2V2 plus V3 ends up being equal to 0. And so you can already determine that this is not going to be a 3-dimensional subspace. The reason it's not a 3-dimensional subspace is we have a non-trivial solution to the equation of like AX is equal to 0 is pretty much what this is saying. And we're going to let W be the subspace of R3 spanned by the vector 1, minus 2, and 1. And so it wants us to show that these subspaces are orthogonal to one another. So if you want to show these subspaces are orthogonal to one another, all you need to do is you need to take an arbitrary vector inside of V, and then you want to do the dot product with 1, minus 2, 1. So if we take an arbitrary element V, so V1, V2, V3, and if we were to dot it with 1, minus 2, 1, you can rewrite this. I mean, maybe this isn't necessary, but just relate it to like this V transpose W we've been seeing. You can rewrite this in terms of matrix multiplication as being V1, V2, V3. So a 3x1 matrix times a 1x3 matrix, 1, minus 2, 1. Right, because then if you did the matrix multiplication, the first row times the first column is this V1 times 1. That'll be minus V2 minus 2V1 and then V3. So this would end up being equal to V1 minus 2 V2 plus V3. And we defined the relation, the defining relation for elements inside of V as this being V1 minus 2V2 plus V3. So by definition of V, this is just equal to 0, right? So this shows if you take any element inside of V and then you dot it with this vector 1, minus 2, 1, you end up getting 0. And so this means that V and W are orthogonal to one another. So V and W are orthogonal. Okay. Yeah, so this is the main claim for this section, or like the main theorem we'll be addressing later on, is we want to prove the following claim, or we want to generalize the following claim, I guess. So if we consider V and W in the previous example, then what ends up holding true is that any vector x inside of R3 can be expressed as x is equal to V plus W, where we have that V is an element of V, and then W is an element of W. And so the idea behind how this works is if you look at our vector space V, it's defined by these relations. We have to have V1 minus 2V2 plus V3 is equal to 0. And so based off of this relation, you can determine at least two elements or vectors that are linearly independent with one another. So like, let's consider the following two vectors. We have V1 is equal to 1, 0, minus 1, and V2 is equal to 2, 1, 0. These are both elements inside of V. You can check, because if you did the dot product of V1 and V2 with 1, minus 2, 1, you would end up just getting the 0 vector. So you can see these are elements in V, and you can also see that they're linearly independent from one another, right? You can't express V2 as a scalar multiple of V1 because you have a 0, the second component for V1, but not in the second component of V2. So these are elements in V that are independent. And so this is going to span a two-dimensional space. But we want to show that any vector x in R3 can be expressed as x being equal to V plus W, where V is equal to V and W is in W. So we want to extend this basis that we have, so that way it's going to make up a three-dimensional space instead of a two-dimensional space. So what we can do is we can consider the row space making up, or with like the row space where this is the first row and this is the second row. So write out like a matrix of the following form. So if we wrote out the matrix 1, 0, minus 1, 2, 1, 0, you can see we have 2 rows and 3 columns. So we're going to get a free variable, right? And we also already said like these two vectors are independent. So we know we'll get 2 pivots. But if you were to row reduce this matrix, you'll get the following. So you'll do minus 2, row 1 plus row 2 would be 0, 1, and then 2. And so you can see that the null space of this matrix has a basis given by 1, 2, 1, right? You add this 1 over to get this 1 here. Oh, this should be minus 2. 1 minus 2, 1, right? So like really we're setting each row equal to 0. So you add the 1 over to get the 1 here, subtract the 2 over to get the minus 2. And then this 1 corresponds to the variable for this free column that we have. So the null space has the following as a basis. I tried to change colors. Okay. So how we can make, and so the key observation is that this 1 minus 2, 1 is exactly this vector we saw before, right? Like this is the vector that spans W. So W was really the null space, or like, yeah, W was really the null space of, I guess, like any system of linear equations that you can create with elements inside of V. And so what we can do is we can adjoin this basis or this vector we found in the null space, and we can just add it to the collection V1 and V2, and that'll end up giving us a basis for all of R3. So what this tells us is that V1, V2, and this vector that is a basis for the null space of our matrix, they end up forming a basis for R3. So we have three vectors that are linearly independent from one another, which means that they're going to form a basis. And so how you could check this, I'm not going to go through with the actual check, but this is something you can do on your own, is you can look at the matrix where the rows are given by V1, V2, and this vector here, and then you can row reduce it, and you should end up getting the identity matrix. So if you took this matrix we had in the beginning, right, these are the first two rows, and now you just add a third row of 1, -2, 1. If you were to row reduce this matrix, you would end up getting the identity matrix. And so that will tell you that the three vectors end up forming a basis for R3, or like a three-dimensional space. So this is something you can easily do on your own. Okay, any questions about what we've been doing so far today? Okay. Yeah, so I'll probably go 10 more minutes and then I'll do the quiz so we can cover a little bit more. Okay, and so we want to generalize this claim that we're talking about. We want to say this is true for any two vector spaces, not just two vector spaces where we have like a specific relation defined for V, and like W ends up being the null space. And so we're going to go through a couple of other facts that really just follow or fall right off from the definition of these spaces. So if we have that A is an M by N matrix, what we want to say is that the null space and then the row space are orthogonal subspaces of Rn. So if you see like the column space of A transpose, you should really just be thinking like this is the row space of A. And so how you can go about doing this is we can let X be an element inside of the null space of A. And so what this implies by definition is that AX times 0, or AX is equal to 0. And so if you were to write this out, what this really implies is you can write out A in the following way. So you can write out A as a bunch of different rows. So this is like row 1 of A. And then we have M rows, so this goes down to row M. And then we're multiplying by X, and this is going to end up being equal to 0, 0, like the 0 vector. And so what this means, if you think about what matrix multiplication is just going to be that the first entry of the product of these two matrices is going to be row 1 dotted with X. The second entry will be row 2 dotted with X. And then all the way down, the mth entry will be row M dotted with X. And so because this ends up being the 0 vector, this is telling us that row 1 up until row M are all orthogonal to row X. So this is telling us that row 1 dotted with X is equal to 0. Row 2 dotted with X is equal to 0. All the way up to row M dotted with X is equal to 0. And so what this is really saying, because the row space is just the collection, like it's a vector space where the basis is just the rows of your matrix, assuming those rows are linearly independent. This is really just saying like the rows of A are orthogonal to X. And so this is saying the row space of A is orthogonal to X. And it's not like we didn't say anything specific about X aside from the fact that X is an element inside of the null space. So really we're just saying like for any element inside the row, like inside of the null space, the row space ends up being orthogonal to that element. So the row space of A is orthogonal to X. Let's see if I can move this up a little bit because I'm running out of space. And so this implies that the row space in the column or the row space in the null space are orthogonal. So the row space is orthogonal to the null space. And one way of writing this, I don't really have much space at the bottom, so I'll just write it to the side, is we have that the null space of A is orthogonal to the row space. So this is a common notation that's going to be used. So this is, sometimes I'll write it like this. I don't know if I have it formally written out in the slide or anything, but this is how you can show the row space and the null space end up being orthogonal. And it's really straight from the definition of the two spaces. Okay, any questions about fact one? Are there questions in the back? Exam. Okay. Yeah, and so fact two, there's another fact. It's really the same as the first fact, except for taking the transpose. So the second fact is saying if A is an m by n matrix, then the left null space and the column space end up being orthogonal subspaces of Rm. I mean, really, this is just the first fact over again. Like the first fact was saying the null space is orthogonal to the row space. And so if you took the transpose, this is really saying that the null space of the transpose and the row space of the transpose are orthogonal subspaces. But if you really wanted to write it out, I'm not going to go into as much detail. But we have that A transpose times some vector y is equal to 0. So we're assuming y is an element inside of the left null space, so the null space of the transpose. So this is really just the same as saying that like the column, like the first column of A transpose, then up until the nth column transpose. If you dot this with y, it ends up being equal to 0, like the 0 vector. That's pretty much the exact same idea over again, except now we're considering the transpose. And so this is saying that the column of 1, like the first column, ends up being orthogonal to y. All the way up to the nth column ends up being orthogonal to y. So this ends up implying that the left transpose or the left null space ends up being orthogonal to the column space. So if you understand fact one, this is really just rewriting fact one, right? So it's not like this isn't really super interesting. Okay, any questions before we do? We'll go through an example really quick. Okay, so I'll quickly go through an example. So this is like, I guess, a common kind of problem. We're interested in 4 subspaces, so it's like it's going to ask you to compute those 4 subspaces. So it wants you to find bases for the null space, left null space, column space, and then row space of the given matrix A. And then it wants you to verify that the left null space is orthogonal to the column space of A, and then the null space ends up being orthogonal to the row space. So what you'll do to begin this problem is you're just going to take A, and then you're going to row reduce it. So we're going to take A, and we're going to put it in reduced row echelon form. So that way we can just read off what the null space is going to be. So to get rid of the 2, you do row 2 minus 2 row 1. So this is minus 1. This would be 0, minus 1, and then 2. So it'd be 1, minus 1, minus 1, 0, 1, minus 2. And then we'll want to get rid of this minus 1 that's above the pivot. So you can write this as being equal to 1, 0, minus 3, 0, 1, minus 2. And you see, we now have something that's in reduced row echelon form. We have these 2 pivots. So we kind of have like this 2x2 identity matrix that makes up the first two rows and columns. And then we have this third column, -3, -2. And so from this, I mean, we can determine a lot of information. We know what the column space, row space, and null space are going to be. So we have that the column space of A, I didn't write this out correctly. So the column space of A, is this going to consist of all vectors of the form of like A times, so we have a pivot in the first column, so 1, 2 is in our basis, plus B. So we have a pivot in the second column, so that tells us -1, -3 is going to be in our basis as well. So this is a basis of the null space. We have two pivot columns. The first two pivots, or first two columns are pivot columns, so we have a basis of 1, 2, and then -1, -3. And then we don't include the -1, 0. The row space, again, you just look at the reduced row echelon form and you see that the first two rows have pivots. So a basis for the row space is just going to be the first two vectors. So this is going to have a basis given by, so any vector inside of the row space can be written as A times 1, 0, -3 plus B times 0, 1, -2. As we discussed on Wednesday, it suffices to just look at the reduced row echelon form when considering the row space. You don't have to go back up to the original matrix A when determining the basis. So this is the column space and the row space. The null space can be easily read off from this matrix as well. So the null space relates to this free column that we have, where we have this -3, -2. And so this is telling us, I mean, you have to do this on the quiz, so I may as well talk about it. So this is telling us that, like, if each of these columns corresponds to a variable, we have x is equal to 3z and y is equal to 2z, right? We're setting these rows equal to 0. And then we have like this one free variable z that we can express x and y in terms of in the following way. And so if we wrote out a generic vector, like I do this all the time, but I think it's the easiest way of thinking about these problems. We can then write out, like, if we have a generic vector x, y, and z, this is the same as 3z, 2z, z. So you can really just say this is like z times 3, 2, 1. And so this vector that we have here is going to be the basis for our null space. So this is equal, so the null space is going to be a collection of all the elements of the form of, it's really just scalar multiples of this vector that we have here, right? So this is going to be all scalar multiples of 3, 2, 1. So from the reduced row echelon form, you can easily read off the column space, the row space, and the null space. Any questions about these three spaces before I do the left null space? Okay, so the left null space is a little bit different. We're just going to take this matrix A, and then we're going to take its transpose, and then we're going to find the null space of that transpose matrix. So it's not going to be like anything too scary or new or anything like that. So if we take the transpose of A, this is, all you do is make it so the first row of A becomes the first column. So we have 1, -1, -1. The second row becomes the second column. So this is 2, -3, 0. And then we just want to put this in reduced row echelon form. So the first row will be 1, 2. We can add the first row to the second. This will give us 0, -1. And then if you add the first row to the third row, you get 0, 2. And you can see now we have two pivots and two columns. So it tells us the null space of A transpose is going to end up being equal to 0. But if you wanted to reduce this to reduce row echelon to be extra sure, you should end up getting the following. Right? You can just add 2 times row 2 and then add it to row 3 to get rid of this guy here. Can add 2 times row 2 to row 1 to get rid of this 2, and then you can multiply the second row by -1. So this is something you can check on your own that you actually end up reducing to the matrix over here. But you don't even have to do that to determine what the null space is going to be, because we already determined we have 2 pivots and we have 2 total columns. So that means the null space of A transpose is going to be equal to 0. So we have the null space of A transpose. This is just equal to the 0 vector. So this is 0, 0. And you can tell we have 2, like it's going to be 2 by 1 because we only have 2 columns. Okay, and then I guess I'm gonna stop here. It also wanted us to verify that these subspaces end up being orthogonal, but I'll do that starting class on Monday. The main thing is you know how to actually compute these 4 subspaces. Okay, any questions about this example before moving on? Okay, I'm gonna stop recording.